Before we make any decisions about model parameters, we need to determine which modeling framework best suits the application. In this video, I will break down the practical differences between continuous and event-based rainfall runoff modeling, what they mean, what they are best for, and where they can be challenging. Stay with me. Continuous rainfall runoff modeling simulates the catchment without interrupting over long periods, months to decades. The model continuously tracks water movement through all storage compartments, including surface, soil, and groundwater, and accounts for gains such as precipitation and losses such as evapotranspiration and deep percolation. These internal state variables evolve dynamically in response to meteorological forcing. Event-based modeling, on the other hand, simulates the response to a specific storm event ranging from hours to several days. The model focuses on transforming a specific rainfall input into a corresponding runoff hydrograph, with initial watershed conditions specified as model inputs or estimated from limited antecedent data. Let's start with the continuous modeling. The key characteristics of this approach are as follows. First, time horizon. Continuous operation over months to decades captures seasonal and interannual variability. Second, initial conditions, generated via warm-up spin-up process and evolve continuously. Third, comprehensiveness. Continuous modeling covers all flow regimes, including low flows, average flows, and floods, enforces water balance, and explicitly simulates soil moisture dynamics, evapotranspiration, and storage changes. Fourth, data hungry. Long simulation periods require a significant amount of high-quality data. Continuous modeling is best suited for the following applications. First, water resources planning and management. Examples include reservoir yield analysis, water allocation studies, low flow analysis, drought assessment, environmental flows, and hydropower operations. Anything that needs the full hydrologic record, not just extremes. Second, climate change impact assessment. Because continuous models simulate evolving storage and losses, they are better suited to test seasonal shifts and long-term water balance changes. Lastly, water quality and sediment modeling. Pollutant loads and concentrations depend on long sequence of events and antecedent conditions, so continuous simulation is the natural framework. The key challenges in continuous modeling are as follows. First, data requirements and quality. Continuous models require extensive, high-quality meteorological and hydrological data over long periods. Therefore, missing data, inconsistent measurement methods over time, poor quality control, limited spatial coverage, and non-stationarity can significantly affect the performance of this modeling approach. Second, computational burden. Long simulation periods create computational burdens, especially for distributed models. This includes the required computational effort to calibrate model parameters and the long simulation time. Best practices are as follows. First, do a serious warm-up. Spin the model until key storages such as soil and groundwater parameters stabilize. Second, calibrate to signature, not only one performance metric. Third, tier your complexity. Start with lumped or semi-distributed models to get plausible states, then refine a spatial detail where it matters. Fourth, automate data quality control and gap filling. And finally, utilize computational resources strategically. Now let's move to event-based modeling. The core characteristics are as follows. First, time horizon. It is generally one storm or a tight cluster of storms, typically ranges from hours to days. Second, initial conditions. They are generally assumed or estimated. Third, targeted focus. This modeling approach generally targets peak flow magnitude and timing, flood volume, and hydrograph shape. Between event processes are not explicitly modeled. Similarly, water balance may not necessarily be met, as evapotranspiration and deep percolation are often ignored. Fourth, computational efficiency. Fast simulation enables rapid scenario iteration. The event-based modeling is well suited for the following applications. First, design storms. Event-based modeling remains the standard approach for designing hydraulic structures and drainage assets such as culverts, spillway, floodways, and detention basins, because regulations often specify a design event for which we need to estimate the corresponding peak flow. Second, flood forecasting and warning. When lead time is short and speed matters, event-based setups are common, often with external information to set initial wetness. The third one is regulatory compliance. Many regulatory applications specifically require event-based analysis. Examples are post-development runoff control, floodplain mapping, dam safety, and environmental flows assessment. The key challenges are as follows. First, initial condition specification. Event-based models require watershed state at a storm onset, but this information is rarely directly measured. This issue becomes more challenging where seasonal patterns are dominant. Second, event selection and definition. Defining event boundaries and selecting representative events for calibration is subjective and impacts results. Best practices are as follows. First, anchor initial conditions to data when it is possible. Use continuous model to supply soil moisture and groundwater states to your event-based model, or incorporate satellite soil moisture products. Second, standardize event separation rules. Define an objective inter-event dry period, stick with it, and document it. Third, calibrate across a diverse event set. Include small, medium, large storms and multiple seasons. Otherwise, you overfit one regime. Finally, be honest about uncertainty. For design, show sensitivity of peaks to initial wetness. It's often the dominant error source. If your goal is to size drainage assets, meet regulatory requirements, or perform flood forecasting, then event-based modeling is usually the right tool. But if you are after catchment behavior in the context of water balance, low flows, climate impacts, or water quality, then you need continuous modeling. And when the stakes are high, don't treat them as competitors, just link them. Let the continuous model fit the initial conditions into your event-based simulation. If you found this video helpful, please share it with others and stay tuned for more videos like this. Thank you for watching. See you in the next one.